talking about sigma notation here today. And sigma notation is just kind of, you've seen the symbol before. It's a funky looking E. That is sigma. This is chapter 13, section 5, sigma notation. Okay, so sigma, it represents the sum. So anytime you see sigma, that means we are going to add some things together. So let's take an example here. Sum k going from 1 to 5 of 2k plus 1. Okay, that is shorthand notation telling us to add up the numbers 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3 plus 1 plus 2 times 4 plus 1 and finally plus 2 times 5 plus 1. Okay, so if you notice right here, k is going from 1 to 5, and I went, my k values, right, k is 2k plus 1, I did 2 times 1, and 2, and 3, and 4, and 5. We literally substituted our k values, 1 through 5, into our formula, which involves k. All right, so that's a straight substitution, and ultimately, yes, there's a little bit of work to do here yet. We're going to do 3 plus 5 plus 7 plus 9 plus 11, which we know is arithmetic. First term's 3, last term's 11, divided by 2. And there are 5 terms, so that comes out to 35. Of course, this is short enough. You could have physically added them yourself. 8 and 7 is 15, and 9 and 11 are 20. 20 plus 15 is 35. But the fact being, if you have a formula to use, you're going to want to use it because I could have went k going from 1 to 1,000, and then you're physically not going to want to add them by yourself. You're going to want to use the formula. We'll get into different kinds of formulas that we have with sigma notation here, but I wanted to get across the meaning of sigma notation. This is shorthand, just like we condensed logs. This is the expanded version, just like we expanded logs. We can condense and expand sigma notation as well. All right, so I could give you a situation, that looked like 3 plus 7 plus 11 plus 15 plus ... all the way up to, let's say 103. Well, hopefully you can recognize this is arithmetic. It has a common difference of 4 and it has a first term of 3. 103 is my last term. I just don't know what n is yet, but I do know my last term is equal to my first term plus the difference times n minus 1. Subtract 3, divide by 4, and add 1. So n is 26. So I can write this situation down, n going from 1 to 26. And now what's my formula? Well, my formula is t sub n. Let me scroll down here a little bit. My formula, sorry I lost some stuff, so I'm going to go forward and back real quick. My formula is t sub n equals the first term plus the difference times n minus 1, which if we simplify that, we get 4n minus 1. So that is my condensed version, my sigma notation for this guy right here. These say the exact same thing. This, physically, you see the plus signs, add them together. This means take the sum of all these values when n goes from 1 all the way up through 26. Okay, so that is sigma notation in a nutshell. Some formulas that we deal with sigma notation. How to quickly add some sigma patterns. So the main ones are the integers. All right, numbers like 1 plus 2 plus 3 plus 4 plus dot dot dot. To add the sum of the integers from n, or I'll go k going from 1 up to some arbitrary number, we'll call it n. We're going to take that number, n, times n plus 1, and divide it by 2. And if you think about it, this should make a whole lot of sense, because this is an arithmetic sequence. And an arithmetic sum, recall, is the first term plus the last term divided by 2 times the number of terms. Okay? Well, here, my first term is always 1. K is starting at 1. So my first term is 1 plus my last term is n. And there's n terms divided by 2. Okay? So these formulas are dependent upon k starting at 1. Okay? K starting at 1 does not mean that this is always going to start at 1, but generally speaking, we can use that to derive our formula. Okay, integers, we can add them up. We can add the squares up as well. So that'd be numbers like 4 plus 9 plus 16 plus 25 plus dot dot dot. The formula for our squares, k going from 1 to n of, oops, I should have put this up top there too, of k squared, this is of k, equals n times n plus 1 times 2n plus 1 all over 6. And finally, we will look at how to add our cubes. The sum, k going from 1 to n of k cubed. It's going to be n times n plus 1 divided by 2. Quantity squared. All right, so those are our formulas. Those are the big guys we're talking about today. Let me highlight them for you. Get a little bigger highlighter here. Sums of the integers, the squares, and the cubes. Example time. Let's say we are asked to add up these numbers, k going from 1 to 100 of 2k minus 1 times 2k. All right. Well, this, I can clean that up a little bit. That's 4k squared minus 2k. Okay, so I'm adding all these numbers up. Now I'm going to do a little bit of work ahead of time here just to explain something that we're not going to do later. If I plug these numbers in, plug in 1, I get 4 minus 2. Plus, now I'm going to plug in 2. If I plug in 2, I'm going to get 16 minus 4. Add, if I plug in a 3, I'm going to get 36 minus 6. And I got room for one more here. So if I plug in a 4, I get 64 minus 8. Dot, dot, dot. That's going to keep going on in the pattern, but notice what's happening here. My first pattern, 4k squared. Okay, I have 4 plus 16 plus 36 plus 64 plus dot, dot, dot. That's all these guys right here. And then I'm going to add all of these guys. Negative 2, negative 4, negative 6, negative 8, dot, dot, dot. Okay, it doesn't matter the order at which I add them. The fact is, I can look at this and I can say it is two separate sigma problems going from 1 to 100. One of them deals with 4k squared. That's these guys, 4, 16, 36, 64. The other one deals with 2k. And that's these guys, -2, -4, -6, -8. Now I pulled my negative out. I could have put plus a minus here, but I just pulled the negative out. So I could really write a minus sign here, and I have all these be positive, right? So I could have done that. But the nice thing now is this is the squares, and this is integers. I have formulas for both of them. I have formulas to add up the squares. I have formulas to add up the integers. So I can do that. Now again, I'm going to do something here ahead of time so we don't need to do it later. 4k squared, as you see, is 4 times 16 times 36 times 64. So that is the same thing as 4 times 1 plus 4 plus 9 plus 16, which means I can add these first and then multiply by 4, which means I can multiply by 4 after I add up all my squares. Same thing's true here. I can pull that 2 out. K goes from 1 to 100. And we're just talking integers here. Scrolling down here a little bit. So let's see what this comes out to. Our formula for the squares. Well, this is 4 times, so equals 4 times. Well, my formula for the squares is n times n plus 1 times 2n plus 1 all over 6 minus 2 times my formula for the integers is n times n plus 1 all over 2. My 1 disappeared from here. I want to go forward and backwards, see what else disappeared. Okay, my 1's back there. It looks like everything else was intact. So this is one of the few times I'm going to allow you guys to use a calculator. We're literally going to plug these values in. Of course, what I'm going to do first, though, is I'm going to reduce 106. Both have a 2 that goes into them, 50 and 3. 201 and 3. 3 goes into 201 evenly because 2 plus 1 is 3. So 201, so that'd be what, like 70 is 210, so that's 9 too many, so 67. 67 there. So I'm going to type into my calculator 200, 50 times 4, times 101, times 67. And that gives me that ridiculously large number. Minus, now this one, 2's cross out, and I have 100 times 101, so that's 101, 100. So minus 10100 equals 1343300. So all those numbers added up. Add up to 1,343,300. Okay, by using the properties of sigma. Okay, last piece here, which you just noticed me using. The properties of sigma say, and we're just going to show, this is just a variable here. That's why I change it from n's to k's to i's. If I have two things I'm adding together, we'll call them a sub I and b sub I. That is, let's put that in parentheses, that is the same thing as adding them up individually. A sub I plus new summation b sub I. And likewise, if I have a constant out in front, we'll call it constant c times a sub I. That's the same thing as adding the stuff first and then multiplying by c. Okay, so you can break these down, and you saw that was helpful because you can change things that kind of look like squares and kind of look like integers into exactly squares and integers. So we did a quick how to expand them, right? Plug in the values and expand it. We did a quick how to put it into sigma notation. Use your formulas from earlier sections to find t sub n, to find n, plug it into sigma. And we did an example of how to actually use the summations formulas for integers and squares, and cubes works no differently there as well. If you have any questions, let me know. Have a good one.